I just recently went past 1 million subscribers here on YouTube, so I want to say a big thanks to everybody. And if you're one of those subscribers, an extra thanks.
And to mark the occasion, I have created a no BS shortcut guide to TIG welding as a free download. The link for the free download is in the description area. It's set up just like a product on weldmonger.com. That's my store, except that it's $0. All you'll need to do is enter just a little bit of information, and it'll take you to a link for your free download. This is more than a cheap, simple workbook. It's actually a video workbook with 10 topics and 10 links to 10 different videos designed to help you learn how to TIG weld better and faster and with less metal. When you click on one of the video frames in the PDF, it's going to take you to a special page with the 10 videos that will give you a great jump start to learning how to TIG weld.
Today's newer TIG welding inverters have all kinds of bells and whistles, all kinds of features. But two of the main things that I look at on a 200 amp TIG welder especially are how low will it start on DC so I don't blow a hole in thin steel, and how thick can I weld on aluminum.
First, the aluminum. I set up a 1/4 inch thick outside corner joint. I set the machine on 190. I'm going to go full pedal. Pretty early on I could see that full pedal is actually just about right. I got 10 more amps I could use, but I don't need it here. And I am using 100% argon. I could even get more out of this machine by using an argon helium mix, but don't really need it here. I was set on around 65 to 70 hertz on the AC frequency, and that worked out okay. So far so good. I have used other 200 amp TIG inverters that kind of struggled on this thickness in this joint. This one didn't. To test out the low amp start, some box cutter blades. I'm not going to weld two together just yet anyway. I'm going to run a bead on the edge. When you're welding on an edge or even near an edge, high frequency pulse settings can help a lot. I'm setting the pulses per second at about 35 or 37, the background current at 30, and I'm going to just try to run a little tiny bead on the very edge of this thing. Not on the sharp edge, just on the regular edges. These are usually about 23 thousandths thick. And normally I would definitely change over to a smaller electrode, but I kept the 332 electrode in there, just sharpened up to a point. Did a pretty good job.
I've been getting some questions on this welder lately, and so I thought the best thing I could do is just put together a video. And I went on my YouTube channel and discovered I have like over 15 videos over the past couple of years since I've been using this welder. I'm going to go over a whole lot of things today, everything from basic carbon steel to chromoly tubing to thick chromoly with a preheat, stainless steel, stainless pulse settings, TIG brazing with silicon bronze, and also testing different frequency settings for aluminum.
First up is 4130 chromoly tubing. It's around 0.63 wall thickness. That's 1.6 millimeter wall thickness. There's a rule of thumb that use 1 amp per 1,000ths of thickness, so I'm at 65 amps here. That's pretty close. It really helps to clean the mill scale on 4130 chromoly tubing. Also helps to have a good cup, a good argon shield. In this video right here, I'm using a Furic Ceramic 12, and that provides a nice big envelope of argon, a nice big shielding area. Prevents discoloration, but also gives you a little bit of leeway on how far you can dip your hot tip of your rod away from the puddle and still keep it shielded. I'm using a 045 filler metal ER70S2. That is usually a really good choice for this wall thickness chromoly.
One of the best tips for stainless is getting moving quickly. Don't hang around and build up heat really slowly, and don't take several seconds to get a puddle going and then get going really slowly at low heat. Get that puddle going, get moving, outrun that heat.
Here we go. I light up. It takes me like about a second to get a first dip of rod in there. That's because I went almost to full amperage almost right away because I didn't want to hang around and build up heat. Always good practice on stainless jobs like this. Travel speed is one of the main factors in heat input. So if you can get going quickly and get moving quickly, you can usually weld at a little bit hotter amperage and put less overall heat into the stainless part. Another thing that can help are pulse settings, and that's up next.
All right, some general principles on pulse. When you use pulse, just know that you're going to need more amperage set on the machine than you will without it.
So I'm going to turn the pulsar switch on and then set my pulse frequency to 1 pulse a second and the background amperage to about 20%. That's going to give me quite a difference in the peak pulse and the background amps. It's going to limit the heat input quite a bit. I'm going to turn my amperage up a little bit here, even though I'm probably not going to need all of it, but I'm going to go up to about 150 and then just control everything with a foot pedal. So I'm just walking over the wire here with the arc, not dipping the rod in and out of the puddle or anything. That's called lay wire, and just pulsing right over it, putting some nice ripples in the bead. That's a really easy way to do a job like this. It's nice to have pulse settings available. Not 100% necessary. It's just one of those really super nice to have things, and when you have it, you definitely figure out uses for it. And this is a good one, really limiting the heat input. All right, let's talk about AC frequency settings and applications now.
AC frequency basically means how often the machine switches from electrode negative to electrode positive within that alternating current cycle. Older machines, you didn't have a choice, but the newer inverter machines like this one, you can set it. And so where do you set it? What's a good setting? 100 to 120 is a good all-around setting, but for me, when I'm using a 200 amp inverter, I've only got 200 amps at my disposal, and if I'm really pushing the limit up toward the 200 amps, I tend to be able to get more heat out of this machine if I set the frequency lower. So for me, lower frequencies on thicker aluminum, higher frequencies on thinner aluminum, or when I really want to pinpoint the arc like welding on an edge.
If you leave the amperage the same, there's a definite difference in the amount of penetration that you'll get at a low frequency versus a high frequency. In my experience, the low frequency is going to get more penetration at a set amperage. Here I'm at 50 Hertz. I'm on a fixed rotator. This wall thickness is about 90 thousandths thick, if I remember right. And at 50 Hertz, this is penetrating all the way through, no problem. I put a camera on the back side so that you could see that molten aluminum just going along real time as I weld along the top of this piece. Penetrating nice and smoothly, evenly, like you would want it to if this was a butt joint. But now if I set that frequency all the way from 50, I'm going all the way up to 250 just to swing the pendulum really far one way, and you can see the difference. It's going to narrow the bead quite a bit. Notice that the tip on that electrode is staying really sharp, like almost like I was welding steel, but it's welding a very narrow bead, which is a very desirable thing sometimes. But if you just want penetration and you want heat input, the most heat input you can get at a certain amperage, which on a 200 amp TIG welder, sometimes you need all you can get out of that max amperage. So if I were to want to run a bead on this, a 1/4 inch wall thickness, and I want a nice wide bead, and I want it to wrap all the way around the corners, I might set this thing at 50 Hertz. That might be a good application for a low frequency when you have the ability to set your frequency. And setting a low frequency, I might also prepare the tip of the electrode to a rounded tip instead of a tapered tip for an application like this, because I want that arc cone to kind of fan out and wrap around those edges. It's really nice to have the ability to adjust the AC frequency. If I were to want to weld 2 or 3 more beads on top of this, I might gradually increase the frequency and maybe even change my tip to a slightly tapered tip. It's nice to have options. So this was a good example of where you might want to use a lower frequency. Let's talk now about increasing the frequency a little bit. The blue area on the AC frequency adjustment there is sort of a recommended sweet spot area. 110 to 140 Hertz. And so that's what I'm going to set it at for this next application. I found it's a really good setting for all around stuff, especially for something like sheet metal like this. This is 063 aluminum, not terribly thin, but thin enough to where you need a little bit of bead control. So I'm using a tapered tip and these settings. And I do like to use a tapered tip on this thickness aluminum and thinner. I get a nice crisp low amperage arc start with a tapered tip, and at 110 Hertz, anywhere from 110 to 140 is a really good setting for this. It gives you a lot of arc control, very little arc wander on the start with that tapered tip, and you can kind of helps kind of narrow the bead a little bit if that's what you're after. A setting of 120 Hertz on the AC frequency is a really good all-around setting if you just want to set it and forget it until you get to something really thick. This is an 1/8 inch thick piece of angle welded to a 1/4 inch thick piece. Doing a pretty good job at 120 hertz here. It's a little business card holder. You can watch the video I did on that a while back if you're interested. So the 120 hertz setting is working out rather well here for this little lap joint. But the next joint is kind of a really wide open outside corner joint because the piece is not at 90 degrees. So it's going to be a pretty wide bead. So I lower the frequency down to 50 or 60. And that's going to fan out the arc cone a little bit and help me to achieve a wider bead, which is exactly what I want right here. I want a nice fat bead that takes it all the way up to those corners. That doesn't make a bit of difference in the strength of this joint or anything like that, but I'm trying to make a nice looking business card holder here that I could leave with a machine shop or something with my business card on there, and would kind of remind them that, you know, I'm not going to screw up their parts. And having done a bunch of work for small machine shops over the years, that is a real concern of theirs when they sub out work. Another good example of having a little bit more arc control at 120 hertz is welding on an edge. Because sometimes you need to build up an edge. Sometimes something was miscut slightly below dimension. You need to run a bead or two on an edge. And it's just good to be able to have that adjustable AC frequency in order to be able to control the arc, do what you want to with it. A common repair in aluminum is filling a hole. So I did this video a while back on an aluminum cube. I ran a bead around there just like I did that edge weld a minute ago, 120 hertz. And then filled the hole in. And that's just pretty easy, but it's not easy if you've never done it or if you're very new to aluminum. So having that frequency control here along with AC balance control just helps things go a lot better. And basically I'm just gradually running bead on top of bead, working inboard. And then when I get to the end, when I get it all filled up, I'm going to give it a little bit more amperage to kind of blend everything together, wash everything together. Add a little bit more rod and then keep that arc swirling so that I don't leave a crater crack, because something like this usually would need to hold air or water, not have a crack, not leak at all. That's a good technique for a hole fill. And then while I was at it, I just decided I would go ahead and run a bead on that outside corner joint, because why not? And it's just another example of 120 hertz is a very useful setting, a good all-around setting for outside corner joints as well as thinner sheet metal joints.
TIG brazing is just what it says. It's brazing, it's not actually welding, so you're not melting the base metal, just the filler metal. In order to do that, you need a good clean surface, free from oxides, free from any crud, any oils or any crud like that. You want a good argon coverage, so using a furic cup like a Jazzy 10 or a 12 really helps a lot. Having that big argon blanket prevents oxides from drawing into the puddle, and pulse. For me, pulse kind of helps limit the heat, therefore limiting the oxidation, and keeps the puddle a little cleaner.
In this video, I was trying to dial in some dead simple pulse settings that worked on silicon bronze. 1 pulse a second with 30% background seemed to work really well. Silicon bronze has a lot of uses. It can be used as an overlay wear material. It can be used to join dissimilar metals like copper to carbon steel and things like that. Super useful to have in the toolbox. Also, it's useful to have good settings that work on pretty much everything, and that's what I was working on here. It's used a lot for artistic stuff and ornamental stuff, and here I was making a hammer, filling in these fillets here with silicon bronze pulsing so it wouldn't run everywhere. And this was on steel, and I was making a Thor dead blow hammer. So I was pulsing here to put the fitting on so I could fill it up with BBs, and afterwards, after everything was done, I sanded and polished and everything to where I'd get a contrast from the silicon bronze to the steel. It's a fun little project. And it made for a pretty cool looking, actually very useful hammer that I'm still using today. Well, let's take a look at some really common welds on plain carbon steel. No pulse or anything like that, just straight amperage and a foot pedal. Got a nice smooth arc, but honestly most every inverter that I've ever used had a nice smooth arc on DC. AC is where they tend to differ a lot. That was the outside corner. Let's take a look at a lap joint. The key to making a good looking weld on carbon steel is start out with clean metal, get rid of all the mill scale or any kind of coating that might be on there. And I'm not just talking about polishing over the mill scale like you might with a wire wheel. I'm talking about removing it with a flap disc or a grinder or something that just gets it all off of there. Hold a nice tight arc. Don't use too much torch angle, and try to keep the hot tip of that rod shielded in the argon. Those are the things that will make a big difference. Up next, we're going to go back down to some box cutter blades, and I'm going to weld them with a 332 electrode just sharpened up to sort of a needle point. This would be better if I dropped down an electrode size to a 16th or even a 040, but it definitely can be done with a 332. I've seen people do it with a 1/8 even. As long as you have that electrode sharpened really sharp and not any rough scratches on it, especially no sideways scratches. It'll help here to use the pulser here. So I'm going to flip the pulser on. I've got it set at 20 amps. That's about twice of what I would normally have it set on. I'm going to set the pulse frequency up around 50 and the background amps just a little over 30. I noticed something when I was welding this first set of blades up here, and that was that my argon coverage just wasn't that great. And I looked over and my tank was all the way down to where it wasn't even reading on the flow meter. And so it came out a little gray. Welded okay, started out okay without blowing the corner away, but it just didn't come out nice and shiny. So I switched over to a brand new full tank of argon, and everything went so much better. It didn't change anything, didn't change the flow rate. My flow was good on the flow meter, so it was actually putting out the same number of CFH, but the quality of the gas just wasn't there toward the end of the tank. I used to do quite a bit of work for small machine shops, and this is one of the jobs that I did a while back. A big, thick chunk of 4130 chromoly. Have no idea what this was going to be, but I knew it needed a preheat. So I preheated to around 500 degrees, set the machine on 165 amps, decided to use what's called a lay wire technique here, which means I just welded it plenty hot, but I walked right over the rod without dipping in and out of the puddle. And that's just one technique that works. It's not always a great technique to use because sometimes you want to be able to see that leading edge of the puddle. But in this case, because I was preheating the part so hot and because I was going to come back over this with multiple other passes, I figured it would be just fine. And it came out looking pretty nice anyway. The cup did its job. Now speaking of cups, there's all kinds of different cups for all kinds of different applications, especially for aluminum. Sometimes you want a small cup on aluminum, sometimes you want a gas lens, sometimes you want a tapered point, sometimes you want a balled electrode. In this case, I rounded the electrode using a number 6 gas lens so that that bead would fan out nice and wide and cover both edges here on this little turntable weld. Back to 120 Hertz. Remember me saying that's a good all-around setting for a whole lot of stuff? Well, coming up, we're going to weld some more aluminum at 120 Hertz using a small number 5 standard collet body cup. A number 5 standard cup works great for an 1/8 inch thick and under aluminum and can save you a lot of gas. That is especially helpful if you're using an argon helium mixture or some other type of expensive gas. All right, we're going back to straight DC now, lowering the amperage, welding on some cold rolled steel on an outside corner joint using chill blocks. Chill blocks can help a lot on discoloration, on distortion, on limiting heat input. They're especially helpful on stainless steel. Pulling that heat out of stainless steel, like I said, it really helps on distortion on a long outside corner joint, clamping those chill bars up like almost right next to the weld. Bars of aluminum work great for chill bars, but I also made a unique little sort of like a copper thing specifically for outside corner joints. That works pretty darn good. I think it's definitely got some room for improvement as far as making it where it maybe swivels a little bit if something's not a true 90, but it works really great for sort of providing an argon trough that traps argon. It gives you a better appearance on your bead, and again, it pulls some heat out of the part. It's just handy for what it costs to build. You could get some copper bus bars or something at a junkyard probably for a few bucks. Wouldn't break the bank. You could also make one of these out of aluminum. Probably a little bit easier to find the material. Well, I hope you enjoyed seeing these video clips, all done using this CK MT200 welder. If you'd like to learn more, visit my store at weldmonger.com and check it out.